Hi everyone. This video is going to teach you how to use antiderivatives to analyze the motion of an object moving in a straight line. First, I'm going to review the terms that we already know that describe motion on a line. Then I'm going to review how to use derivatives to analyze motion along a line. And finally, we will use antiderivatives to solve some motion problems. As you recall, the position of an object is its location. We usually write an object's position as s of t, meaning that its position is a function of time t. Sometimes the symbol x of t is used to describe horizontal motion, or y of t is used to describe vertical motion. Velocity refers to the derivative of position with respect to time. V of t equals s prime of t. The speed of an object is the magnitude or the absolute value of the velocity. The sign of the velocity has special significance. If the velocity is positive at a given time, then the particle is moving to the right at that time. If negative, the particle is moving to the left. And if the velocity is zero, we say the particle is stopped. If we think about this in first derivative terms, we're saying that if s prime is positive, then s is increasing, and vice versa. Finally, the acceleration of an object is the derivative of the velocity with respect to time, which makes it the second derivative of the position. The sign of the acceleration can be a little bit tricky to read. If the acceleration is positive, then the velocity must certainly be increasing, but this does not mean that the speed is increasing. The graph below shows the velocity of a particle in red and its speed in green. You can see that the graph has a positive slope or a positive acceleration for all times, but the speed is only increasing for t's greater than t1. We saw previously in class that we can read the sign of acceleration like this. If the acceleration and velocity have the same sign, the object is speeding up. If they have opposite signs, the object is slowing down. Let's use a problem to review how we can use derivatives to analyze motion. Consider this situation. A car moves in a straight line with a velocity v of t given by 1/10 negative t cubed plus 3t squared for t's between 0 and 5, with time t measured in seconds and velocity in meters per second. The car starts at the position s of 0 equals 0. And now we ask several questions about the car. A. Find the times for which the car is stopped. B. Find the times for which the car is moving to the left. C. Find the acceleration of the car at t equals 3 seconds. D. Find the absolute maximum speed of the car. And E. Find the time for which the car is furthest to the right. Let's take each of these questions in turn. A. Find the times for which the car is stopped. Now stopped means that the velocity is 0, and so we set the velocity equal to 0, and we solve the equation, remembering that factoring is our friend. This gives us two solutions, t equals 0 and t equals 3, and so we present our solution: the car is stopped at t equals 0 or t equals 3 seconds. The work that precedes justifies our answer. Also, we can take a look at the graph of the velocity, and we see that the velocity is 0 at t equals 3 or t equals 0 seconds. B. Find the times for which the car is moving to the left. For this, we want to consider the sign of the velocity, and so we create for ourselves a number line showing the signs of the velocity. If we have the graph of the velocity, we can read those signs directly off the graph. If not, then you can choose a representative value from each subinterval. T equals 1 is a good representative value, and t equals 4 is another one. You can plug those in for yourself to see that the velocity is positive between 0 and 3, and negative between 3 and 5. Notice that we respect the domain restriction that was given in the original problem, so we stop our solution at 5. And so we say the car is moving left during the interval 3 to 5 because the velocity is less than 0 or negative during those times. Notice that the endpoint 3 is not included because the car is stopped at that time, which is not the same as moving left. C. find the acceleration of the car at t equals 3 seconds. Since acceleration is the derivative of the velocity, we take the derivative of our velocity and then evaluate at t equals 3 to get -9/10 meters per second squared. Notice the units on the acceleration are meters per second, or meters per second squared, because we took a derivative of a quantity that had units meters per second. If we sketch a line tangent to the graph of v at t equals 3, we can see that it has a slope that is consistent with our computed value of -9/10. D. Find the absolute maximum speed of the car. Now, an absolute maximum has to occur either at a critical point or at an end point. The critical points are exactly those places where the derivative of the velocity is equal to 0. So, we take the derivative of the velocity that we previously computed, set that equal to 0, finding two critical points, t equals 0 and t equals 2. One of those, t equals 0, happens to coincide with an endpoint, which is nice because it reduces the amount of computation that we need to carry out. And so we compute the absolute value of v of 0 is equal to 0, the absolute value of v of 2 is equal to 2/5, and the absolute value of v of 5 is equal to +5. This is the largest, so we report out our answer. The absolute maximum speed is 5 meters per second at t equals 5 seconds. Notice that in this case, our maximum occurred at one of the endpoints rather than at a critical point. The graph of speed and velocity confirms our answer. You can see that the largest speed happens over at t equals 5. E. Find the time for which the car is furthest to the right. Looking back at the number line we had from part B, we can see that the velocity is positive, that means the car is moving to the right, from 0 to 3, and then the car stops and begins to move left from 3 to 5. If you can picture the motion in your mind, you can see that means that the car is going to be furthest to the right at t equals 3. So we report out our answer. The car will be furthest to the right at t equals 3 because velocity is positive for t less than 3 and negative for t greater than 3. Notice that this looks exactly like the argument for an absolute maximum, and it is. Furthest to the right is just another way of saying maximum position. Now we would like to use an antiderivative to further analyze the motion of the car and answer some additional questions. F. What is the position of the car for t between 0 and 5? G. What is the maximum furthest right that the car reaches? And H. Where is the car at t equals 5 seconds? An antiderivative can help us to answer these questions. We can think about question F like this. We already have the derivative of s, which is the velocity, and we also have a condition on s, which is s of 0 equals 0. So we can immediately write our solution as s of t equals the antiderivative of the velocity. Take a moment to check that this is the proper antiderivative. Once we have that antiderivative, we can apply our condition, s of 0 equals 0, to find that c is equal to 0, and this gives us the final answer, s of t equals -1/40 t to the 4th plus 1/10 t cubed. The animation to the left shows what the motion of the car would actually look like to an observer standing outside. As time increases, first the car goes to the right, and then at t equals 3 it turns around and goes back to the left, reaching a maximum speed at t equals 5. G. What is the furthest right that the car reaches? We already found earlier that the car reaches its furthest right position at time t equals 3. So it's a simple matter of finding the position at that time, s of 3. Plugging in, we find that s of 3 is equal to 27/40, or a little bit greater than 1/2 of a meter. The graph below shows the path of the car together with the graph of the velocity. You can see that right when the velocity changes sign from positive to negative at time 3, the car reaches its furthermost right position, which is a little greater than 1/2 of a meter. Finally, where is the car at t equals 5 seconds? This is simply asking a question about the position again, and we already have the position equation s of t equals negative 1/40th t to the 4th plus 1/10 t to the 3rd. Plugging in t equals 5, we get our solution. S of 5 is equal to negative 25/8 meters. The negative sign indicates that the car is to the left of the origin, which is exactly what we see from the animation. Let's consider another problem where we can use an antiderivative to analyze motion. A rock is dropped from the top of a 64-foot high building. It falls with a velocity v of t equals negative 32t for t greater than or equal to 0, with velocity measured in feet per second and time measured in seconds. How fast will it be going when it hits the ground? Now we observe that hitting the ground means that its height, y of t, is equal to 0. And the given information can be read as y prime of t, the velocity, equals negative 32t, and y of 0 is equal to 64 feet, where the rock is when the problem starts. This is exactly the information that we need to find y of t. Y of t is the antiderivative of y prime of t dt, in other words, the antiderivative of negative 32t dt, which is negative 16t squared plus the constant c. Applying the condition, y of 0 is equal to 64, so c is equal to 64. Putting it together, we have y of t equals negative 16t squared plus 64. This gives us the height of the rock at any time t. Now, as we said earlier, the rock will hit the ground when the height is equal to 0. So we set y of t equal to 0 and solve, either using factoring or else a simple square root, and find that t is equal to either 2 seconds or negative 2 seconds. We reject negative 2 seconds as being out of domain. Now the question was, what is the speed when the rock hits the ground? And so that would be the absolute value of the velocity at 2 seconds, which is 64 feet per second. To recap, we can use antiderivatives to find position from velocity. We can also use them to find velocity from acceleration. Some of your homework problems will have you doing that. The reason is very simple. Since velocity is the derivative of position, position is the antiderivative of velocity. Since acceleration is the derivative of velocity, velocity is the antiderivative of acceleration. Take care.